Hi everyone. So this is Advanced Calculus, our third lecture. So in our last lecture, I kind of finished at projection operators and defining the idea of projecting a vector onto another vector. So let me recall that, and then we will give some examples and some applications of this projection operator. So overall, we are still doing dot products, right? So we are still on dot products. So let's recall then. Projection. So I call it projection operator. I mean, perhaps your book maybe has another name for that, but that's the same idea. So, but the idea geometrically is very, very interesting. So you have this vector B that you're projecting on, and there is vector A that we want to project it onto B. And the idea was that if you take this line, and from tip of A, you drop a line perpendicular to this line B in the same plane that A and B are located, right? Okay, so this is orthogonal, and you end up with getting a new vector here. So we call this projection of A along B. So this new vector is along B, and it's geometrically defined like that. So imagine, for example, this angle is theta, but right now it doesn't matter what the angle is. And we derive the formula for this thing, which is a very important formula. The formula we derived is proj A along B was equal to A dot B over norm of B squared times B. By the way, this quantity, I keep calling it norm. This is kind of more professional term for this, but you can equally, and actually that's also professional, to call it magnitude of B. So let me write it once at least. I keep calling it norm of B. Another name for that is magnitude of B. Of course, we know what it is. Geometrically, it's just length, right? So you can call the same notion with three different names: norm of B, magnitude of B, or length of B. It doesn't matter. So that's the formula. I mean, that's we derive this formula using definition of dot product and all that, right? So that was the formula. Okay. One of the things we can do with this formula is, so we can completely actually decompose this vector A on this line and on a line, again, on the same plane, which is orthogonal to line B, vector B. So if you draw this line here, perhaps maybe I should correct it a little better. Okay. So you get this vector n now. So we are going to write A as sum of this vector, which is proj A along B plus, and of course this vector is obviously A minus proj A along B, right? So, so we have this interesting, important formula. So when you look at this formula, of course, it looks like a trivial thing. I mean, you can, of course, always say A is equal to some vector plus A minus that vector. So, I mean, verifying this is trivial the way it's written, right? It doesn't. It looks like it doesn't entail anything to verify this. But in fact, this is very interesting because of the geometry of the situation, right? So we know that, so let me just note that by the way we constructed these two vectors are orthogonal to each other. So I just write like this: proj AB is orthogonal to A minus proj AB, right? You can verify this using the definition. It's a nice exercise to do it that way. Or you can trust the geometric intuition that we use to develop this thing. So either way, this is true. And so this is, remember, our notation for orthogonal. Okay. Now, this is called the orthogonal decomposition of vector A along B and orthogonal direction. So this is N. So let me write it like this. A, in other words, we have decomposed it as proj A along B plus N. We can write this in this form. So where N is, of course, A minus proj AB, right? So this is a very useful way of decomposing a vector into sums of two vectors. I mean, yeah. Well, this one is along an arbitrary vector. The other one is orthogonal in the same plane, and so on. So that's something quite useful. It's also called resolving. So we say A is resolved as a sum of two orthogonal vectors. Okay. So that's well, and these two things are called orthogonal components of A. So that's what we have done so far. Now, some more ideas about this. One of the ideas is, you see, let's look at these three vectors. So the unit vectors I, J, and K. So these three unit vectors are coordinate bases, so to speak, I, J, K. So you see they have the property that they are orthogonal to each other, right? And they have unit length. So we just write this as these rules. I dot I is equal to 1. I dot j is equal to 0. I dot k is equal to 0. And you can also do the same with j. You just say j dot I is equal to 0. J dot j is equal to 1. And j dot k is equal to 0. Again, with k dot I is equal to 0. K dot j is also equal to 0. And k dot k is equal to. So you get a kind of nice matrix, 3 by 3 matrix, where on the diagonal this is just 1, and off diagonals is just 0 or zeros. So this is called, so we just say ijk is an orthonormal frame or orthonormal basis, is an orthonormal basis or frame for the space R3, right? For our space R3. Let's check my time. Okay, so yeah, this is the ideal orthonormal frame. But the point is that you don't have to have just ijk. You can have basically a lot of different vectors that would form an orthonormal frame. So all you have to do is just to rotate ijk together in a space in any which way you want. You're just rotating it as a solid object. The three vectors, ijk, you don't change the relations to each other, but you rotate this, and of course keep the center, keep the base at the origin. Just rotate it. And you end up at some other triples of vectors, like E1, E2, E3, that would satisfy these relations. So let me just write this down, because that's a nice application of dot product. So we just say, in general then, any three vectors, say E1, E2, E3, that satisfy relations E1 dot E1 equal to 1, E1 dot E2 equal to 0, E1 dot E3 equal to 0, E2 dot E1 equal to 0, E2 dot E2 dot E2 equal to 1, E2 dot E3 equal to 0, and E3 dot E1 equal to 0, E3 dot E3 equal to 0, E3 dot E3 equal to 1. You see, this is completely similar to this, right? Except that we are not using IJKs, the standard basis. We are using a new basis, E1, E2, E3. So this could be your original IJK, but then now we have got this new ones, E1, E2, E3, right? So this is your IJK vectors, and this is your new orthonormal vectors. Again, these three are orthogonal, and they satisfy this relation. There's no other condition. Now, you might wonder, what's the use of this idea, the orthonormal frames? The use of this idea is that if you have an orthonormal frame, then you can write any vector in terms of these things very easily, and without having to solve systems of equations in order to present a vector as linear combinations of those vectors. So let me give you an example of this. You can start from IJK and then doing some appropriate changes to this, and then you get the vector 0. So for example, let's take E1 equal to 1 over root 2 I plus j, E2 equal to 1 over root 2 minus I plus j, and E3 just to be k. So I ask you to do it at home when you're watching this. Check that these relations, the stars, are satisfied. Holds. And also make sure you understand the geometry of this, these three vectors, E1, E2, E3 in this example, right? So what is the geometry? Geometry is that we have really rotated ij in the same plane and kept the third vector unchanged. So we have done a rotation in IJ plane, right? So let me write it down. Maybe draw a picture for you here, perhaps. So the vectors in IJ plane, IJ. Now this E1, E2 is like this. This is you draw, and then the E1 is a unit vector in this direction. So if I just draw a vector from this corner to that corner, it's going to have length √2 by Pythagoras. So you divide by √2. That's what we did, right? So this is going to be a vector like that. So this is going to be equal to, you know, it's 1 over, so this is like E1 in my notation. And the other one, E2, okay, maybe this is not the scale, maybe this is a bit better. Okay, this is E2. So what you have done, you have taken IJ and rotated it by 90 degrees. So this is E1, E2, of course. Yeah. Of course, you could have chosen E2 and not along this line in the opposite direction. That would do the same. That would also be fine. This is also, maybe I'll call it E2 prime. This would be E1, E2 prime, and E3 also is an orthonormal frame. E1, E2 prime, E3 is also an orthonormal. So maybe I should say okay, so yeah, orthonormal frame or basis. Okay, so this is now what is the difference between basis E1, E2, E3 and the basis E1, E2 prime and E3? E1, E2, E3 and E1, E2 prime and E3. So the difference between both of them are orthonormal frames, orthonormal bases, but there is a subtle difference between the two. Okay, so let me just write it here, and then we will discuss it more. I want you to pay attention to this fine point. So I just say it like this: a subtle difference between frames E1, E2, E3, as I have depicted there, and E1, E2 prime, E3. So the difference between these two bases is that the first one has the same orientation, or in other words, is right-handed, same orientation as the original orientation of the space, which is IJK. The second one has a different orientation, it's the opposite orientation. So I just say it like this. This guy is right-handed. This guy is left-handed. So you can talk about hand. So the idea here is handedness. Another terminology for handedness is orientation. And another term for this is chirality or chirality. These three words, you may see these things in your physics courses, in your chemistry courses, in math courses, for example. In mathematics, they mostly use orientation. In physics, they use chirality and also handedness. In chemistry, they use both to describe different situations for molecules. Okay, so I want you to pay attention to the fact that this basis, E1, E2, E3, has the same orientation or handedness as IJK, right? And the reason is this so-called right-handed rule. So imagine this is IJK, and we have just done a rotation from this. So in other words, so let me maybe explain this right-handed rule, or right-hand rule. You can look at the pictures in the book. So the idea is that if you put your thumb on E1 and E2, so if you rotate from E1 to E2 by right hand, your thumb should be directed along E1. So let me write it. Rotate your hand, your right hand, of course, your right hand from E1 to E2, so to speak. And you notice that if you do that, you're forced to point your thumb finger along E3. And then your thumb is along E3. That's the first one. But for this one, if you want to move your hand, your right hand, moving E1 to E2 prime, you notice that your thumb is going to go the other direction, the opposite direction, not E3 or I, or J, or K, I'm sorry, not E3 or K. So this is left-handed, and the first one is right-handed. So I want you to think about this idea of handedness as they appear. So we just say that, did I say that? Yeah. Okay, so let me just say that E1, E2, E3, and I, J, K are right-handed systems, but E1 prime, sorry, E1, E2 prime, as I defined it over there, and E3 is left-handed. So that's a kind of subtle, fine point that is going to show up very soon. So we have to pay attention to this. Okay, so another point of these orthonormal frames I wanted to emphasize is that I said that you can write any vector in terms of these three vectors very easily. So let me give you an example, then the idea will transpire very easily to you. So here's an example. Okay, so here's an example. Express the vector say, I just call this vector maybe 1, minus 1, 3 as a linear combination of vectors E1, E2, E3. So what's at stake? What's at stake is the following. So we just want to write down so the idea is the following. So solution. Want to find. So we want to write 1 minus 1, 3 as linear combinations of these three vectors, say lambda 1, E1, plus lambda 2, E2, plus lambda 3, E3. So we want to find lambda 1, lambda 2, lambda 3 such that this holds. Of course, one way to do this would be to say, okay, I know my vector. I know E1, E2, E3 in terms of coordinates. So 1 over root 2, I don't know, I plus j it was, and so on. And then you get 3 equations, 3 unknowns, and you solve it. Okay, that's fair enough. But imagine you had 100 of these equations. I mean, sometimes you are dealing with data in a huge space, like 200 dimensional space. And still you want to write your vector, which has 200 components, as linear combination of another 200 component, another 200 vectors, for example, right? So how would you do that? And that's where the idea of orthonormal frame or orthogonality comes very handy. So the solution is then you just multiply, take a dot product with E1. So we just say that E1 is equal to this one dot E1. But now this is very easy to find because E2, E1 is 0, E3, E1 is 0, E1, E1 is 1. So this is equal to lambda 1. And all you have to do, you have to take the dot products. Your lambda 1 is already solved. You just take dot product. So this is equal to, so we get that 1 minus 1, 3. Remember, E1 was 1 over root 2. This was I plus j, which is 1, 1, 0, right? So that's equal to lambda 1. Well, of course, I mean, you can easily find the value here. This is 1, so this is 1 over root 2. And actually, this one is minus 1 over root 2, right? So lambda 1 is equal to 0. Okay, so that's cool. Cool. I mean, then we can find lambda 2 and lambda 2. Similar. So that's a very important idea. I want to emphasize on that. Using dot product and the idea of orthonormal frames, you can really solve some interesting problems without having to solve linear equations. You can just take dot product and then result will come out very easy. So that's one issue that I wanted to discuss. So now let's see what else. Oh yeah, there's an application of the idea of dot product to physics. Very, very fundamental, basic application. That's the idea of work, right? So I have to tell you about this. So work is a dot product. You have seen this in your physics courses, I'm sure. So let me just, but I have to tell you this anyhow. So imagine you are pulling a kind of shopping cart, a big one. So, and then you have this force F applied to your shopping cart, and you're moving it in a direction, of course, is parallel to the ground, and with the amount L, vector L. So you're moving from P to Q. So you get a vector L. That's how much you have moved your shopping cart with force F applied in this direction. Of course, I mean, you can apply force in any which way you want, right? So here, I'm like pulling my shopping cart in a kind of a strange way. like that. But that's what it is. So then the work W that's done by F in moving my shopping cart from P to Q is by definition equal to F dot L. Okay, so that's so we say this is the work done by F in moving the shopping cart from from P to Q, sorry. Yeah, okay. So there may be some problems that relate to this notion of work. So just want to make sure that this discussed. Okay. So now we are moving to a new section, which is cross products. So this is cross product. So the idea of cross product is that now this time we have two vectors and we are not going to produce a number, which was the dot product before, right? We're going to produce a new vector, right? So there is this vector A and this vector B. And we are looking for a vector C that has some properties. So I will write down kind of properties that we are looking for, our cross product, and then we'll see if this problem has a solution or not, right? So that's what. So we are looking for a vector C. So given, so let me write it like given vectors A and B, we are looking for a vector C such that, so when I write ST, it means such that. Perhaps you have, maybe I have already used it. Yeah, I have used it here, at least one. So ST means such that. We are looking for a vector C such that it has the following properties. First of all, C is orthogonal to A and C is orthogonal to B. So remember, this was our notation for orthogonality, so it's orthogonal to both of them. Okay, so that gives us already the fact that this C has to be along a line which is orthogonal to the plane that contains A and B. So this already is very valuable information. But of course does not define C completely because, well, it's on this line, but what is the magnitude of C, for example, right? So still the magnitude is not fixed. Second, the magnitude of C, now I'm saying, is equal to area of this, of the parallelogram formed by A and B, which we know what the area is. Well, I mean, from elementary geometry and these things, we know that, or you can even try to prove it yourself. If this angle is theta, this is equal to length of A, length of B, times absolute value of sine of theta, right? Okay. So it's a positive number because it's magnitude or length. So I should put absolute value sine. Just be careful Don't put just sine of theta, because sine of theta, when theta is bigger than 90 degrees, can be negative, right? It's negative, definitely, right? So make sure to put absolute value sign over. So now the question is, does 1 and 2 completely define C now? Right? So that's the question. So we have given now the direction of, in other words, we have given the line that contains C, and we have given the magnitude of C. But the point is that 1 and 2 does not completely fix C. Because C might be in this direction or in the opposite direction with the same magnitude still, right? So the point is that we have to say which direction you choose, right? And that's where the idea of right-handed systems, right-handedness or orientation and right-hand rule comes in. So the third property then is that A, B, and C, again, with this order that I'm writing, form a right-handed system. Or right-handed frame, well, A and B has to be linearly independent, but that's okay. In generic case, we can say that system. So what does this mean? It means that if you put your hand like this, and you move your palm from A to B, your thumb should be in the direction of C. So this is the right thing. If you were to draw the opposite direction, that wouldn't be a right-handed, right? Because to go from A to B, your right hand thumb inevitably directs in that direction, not the opposite direction. So that's the, so somehow the human physiology fixes this mathematical concept, which is strange, right? So it's why we should rely on human physiology. What if all peoples in the world wake up tomorrow and then notice that actually their thumb is pointing in the opposite direction? It would be. It has never happened before, but who knows? Okay, I'm joking, but it's kind of strange. Just think about it, that we are defining some concept based on some human physiology. But the thing is, actually, you don't have to do that. So you can get a little more subtle and say that ABC has the same orientation as IJK. So that's a mathematical, precise, waterproof definition of what this direction of C is. We just say that it should have the same orientation or same handedness as the original standard basis. So let me write it down, because that's kind of useful actually to know. Usually this definition, more mathematical, more abstract definition I'm given, is not taught because right-handed rule is kind of useful, but let me just say it anyhow. Alternatively, phi can be expressed as so we just say A, B, C has the same handedness same word, handedness or orientation. You can say chirality or chirality as well, has same handedness as the standard basis ijk. Okay. So we can, so because ijk is kind of fixed, it's independent of any property of humans or anything else. It's just mathematical context, because I is, remember, is this one. Everybody, you can tell your computer even what I is, right? J is 0, 1, 0, and K is 0, 0, 1. I mean, sorry, 0, 1. So you can just code these three vectors into your computer, and then your computer can do computations without knowing anything about whether this is up or down or something. Just so this is a completely well-defined concept. All right, so these are the three properties. Geometrically, you see that actually such a vector C exists, but we will also write down a formula in the next lecture for this. But for now, let me just fix the notation. So the notation is that C is denoted by A cross B. So A cross B, the cross product of A and B. So that's a very important notation. So now I can write 1, 2, 3 in the following form, right? These properties 1, 2, 3, we can just write it as, okay, so says that A cross B is orthogonal to A, and A cross B is orthogonal to B. That's nice. Very good. And second property is that actually magnitude of A cross B, we said, is equal to the area of this parallelogram, like that, right? Formed from by A and B. So this is magnitude of A, magnitude of B, absolute value of sine theta. That's property 2. Now, property 3, I cannot write it like a formula. It just says, so 3 is as before, really. So now, there are some immediate consequences we can say from these things. One of the properties is that if you change the order of the cross product, the value of the cross product is going to change. It's going to be negative vector, right? So now let me write it here. This property, so just write it like this. Note that 3 implies that A cross B is equal to minus B cross A. Okay. Because if you change the order, you follow the thumb rule, you are pointing your finger in the opposite direction. That's very easy to verify. Okay. So, okay, so that's what it is. So another one also. So we say that. So let me just write it. We just say that the cross product is not commutative. So let me note that. So unlike dot product, the cross product is not commutative. Changing the order will result in changing changing the value by sign, but still is a change. So signs are really important. Now, another thing is that if you take cross product of A by itself, what happens? Let's see what happens. So this is a property, maybe I just say A note, so also, we should note that A cross A is equal to 0 for any vector A. So what's the proof of this? How can you prove this, or prove this, I mean? Just think about it for a moment. How can you show that, by just knowing this much, how can you show that A cross A is equal to 0 for any vector, no matter what? Okay, so the answer is, well, there are two ways you can actually do that. Let's look at the first method. I mean, my first method is to use this, you see. So proof. Okay, so this relation star, if in a star I just put B equal to A, choose B equal to A. If you choose B equal to A, then we get A cross A equal to minus A cross A. So from here you get that A cross A is equal to 0. A vector that's equal to its negative is of course going to be the 0 vector. But you may complain, and you would be right to complain about this proof, because you might say that, okay, but this rule you were able to verify by assuming that A and B are different, because you said that you're going to move your hand by your right hand, you know, from A to B, and that's a valid point. So this proof is not completely okay using this definition. So let me give you another proof, which is okay using property 2. So better proof now, I just say. Just use 2. Use the area law. Okay, I mean, if A coincides with B, this parallelogram formed by A and B is just a line, is area 0. A equal to B implies that area is equal to 0. So you're done. So that's a better proof. But the first proof also can work if you verify this condition for all A and B, and this is actually what we're going to do. Algebraically, we're going to derive a formula which is independent of any picture, and then we will verify that all these properties are satisfied. In that case, then that proof is okay. Okay. So guys, thank you so much. This was our third lecture, and in our next lecture, what we're going to do, we are going to give a formal algebraic definition or alternative definition of cross product. We will use some of these properties to show that cross product has some beautiful, reflects some beautiful geometry of three-dimensional space. And with that, we can use a lot of computations, writing equations for different shapes and configurations in the space, in three-dimensional space. So the two things together, the dot product and the cross product, they capture a lot of geometry of Euclidean geometry of three-dimensional space in a very algebraic, very nice way. So this is a very valuable tool. So thank you very much. Have a wonderful day. And I just turn off my video. So which one is it? Pause, stop. Okay, so.